400,000 years after the Big Bang, the universe was a dark, formless soup of hydrogen and helium, too hot and too uniform to have built a single star. According to the best model cosmologists have, the one that has successfully predicted the large-scale structure of the universe for decades, it should have taken hundreds of millions of years of slow, patient gravitational collapse before that soup organized itself into the first galaxies, and hundreds of millions more before anything resembling a large, structured, mature galaxy could exist. Then, the James Webb Space Telescope opened its eye on the deep universe, and it found galaxies that were not supposed to be there yet. Big ones, bright ones, structured, orderly, almost adult-looking galaxies sitting at a point in cosmic history when the universe itself was barely 3% of its current age. This is the story of what astronomers have started calling, only half-jokingly, the impossible galaxies problem, why it has pushed some of the most respected cosmologists in the world to openly question pieces of a model that has otherwise worked remarkably well, and what it actually means, and does not mean, to say that a telescope has shattered physics. To understand why this finding landed as hard as it did, you first have to understand what astronomers expected to see when the James Webb Space Telescope, launched on Christmas Day of 2021 and fully operational by mid-2022, finally turned its enormous gold-coated mirror toward the most distant reaches of observable space. Webb's primary mirror spans 6.5 meters, built from 18 hexagonal beryllium segments, and collects more than 6 times the light of the Hubble Space Telescope's smaller mirror. Just as importantly, Webb was built to see primarily in infrared light, a deliberate design choice tied directly to one of the strangest and most useful facts about an expanding universe. Light from extremely distant, extremely ancient galaxies has been stretched over billions of years of cosmic expansion from the visible wavelengths it started as into the infrared by the time it finally reaches us. To see the very earliest galaxies at all, you need an infrared telescope. Webb is, by a wide margin, the most powerful one ever built. The prevailing cosmological model going into Webb's launch, known as Lambda-CDM, describes a universe built mostly from dark energy and dark matter, with ordinary visible matter making up only a small fraction of the total, and it makes fairly specific predictions about how quickly structure should have assembled after the Big Bang. Stars needed to form first, in the earliest, smallest clumps of gas dense enough to collapse under their own gravity. Those first stars needed to live, die, and seed the surrounding gas with heavier elements. Small proto-galaxies needed to merge, gradually, patiently, into larger ones. It is a model built on slow accumulation, and within its framework, finding a large, massive, well-structured galaxy within the universe's first few hundreds. Million years should have been, if not strictly impossible, then at least vanishingly rare. Within Webb's very first year of science operations, that expectation ran directly into the data, and the data did not cooperate. Astronomers identified galaxy candidates at extreme redshifts, the measurement cosmologists use to gauge both distance and cosmic age simultaneously, and spectroscopic follow-up work, the painstaking process of confirming a candidate's distance by analyzing its precise light signature rather than relying on brightness and color alone, verified multiple galaxies that existed when the universe was only 300 to 400 million years old. The most ancient galaxy identified by Webb to date existed a mere 280 million years after the Big Bang, a number that becomes almost dizzying once you sit with it. Less than 2% of the universe's entire current age. These were not the faint, formless smudges of protogalactic material the standard model predicted should dominate this era. Many of them were surprisingly bright, notably compact, and in several documented cases showed real internal structure, the kind of organization astronomers associate with galaxies that have had considerably more time to mature. Researchers studying this population have identified 3 separate categories of objects that have proven especially difficult to reconcile with existing theory. So-called little red dots, small, extraordinarily compact, deeply reddened objects that were never observed before. Webb came online, but have since turned up. By the hundreds in its deep field images, first appearing in significant numbers, roughly 650 million years after the Big Bang, their exact nature, whether dominate D, by unusually dense star formation, or by rapidly growing black holes, still a subject of active debate. A second category, nicknamed blue monsters, describes ultra-compact, yet remarkably bright early galaxies whose brightness implies a stellar density far higher than standard models of star formation efficiency comfortably allow. And in November of 2024, a separate team identified 3 ultramassive galaxies, each nearly as massive as the entire Milky Way, already fully assembled within the universe's first billion years. A scale of mass that most pre-Webb models did not expect to see fully built until considerably later in cosmic history. The puzzle deepened further in January of this year when a team of researchers, including scientists from Texas A&M University, identified something even harder to explain than a single early, oversized galaxy, an active merger event. At least 5 separate galaxies in the process of colliding and combining into one, captured just 800 million years after the Big Bang. Complex multi-galaxy mergers of this kind were expected to be a phenomenon of the universe's middle age, not its earliest childhood. One of the researchers involved put the implication plainly. Findings like this mean the working theories of how galaxies assemble themselves and how quickly that assembly happens need to be updated to match what is actually being observed, rather than what earlier models assumed should be there. Then, in May of this year, came a discovery that struck at an even more fundamental assumption. A team led by researchers at the University of California, Davis, examined a distant early galaxy, cataloged as XMM-Vid1-2075, and found something that, according to nearly every existing model of how galaxies grow, should not have been possible at that stage in cosmic history. The galaxy displayed almost no rotation at all. Its stars, instead, moving with a kind of strong, disordered, random motion typically associated only with very large, dynamically mature galaxies, found much closer to Earth, galaxies that have had billions of years to settle into that kind of behavior. Finding it in the early universe, alongside 2 comparison galaxies from the same era, one of which did show clear, orderly rotation, and another which displayed a more irregular structure, gave researchers a genuinely rare side-by-side look at just how differently early galaxies can behave from one another, and how far the behavior can diverge from what a simple, one-size-fits-all model of early galaxy formation would predict. None of these individual findings, on their own, would necessarily count as headline-worthy. Astronomy has a long history of individual outlier objects that eventually get folded into a slightly revised, only mildly adjusted version of an existing model. What makes the current moment feel different, and what earned Webb's early universe findings the reputation of genuinely challenging cosmology, rather than simply adding an interesting data point to it, is the sheer accumulation of similar surprises arriving from independent research teams using independent methods, pointed at independent patches of sky, all converging on the same broad, uncomfortable conclusion. Galaxies in the very early universe are, collectively, bigger, brighter, more structured, and more dynamically mature than the standard model expected them to be. And this is not a pattern showing up in one anomalous object. It is showing up across dozens of them. Cosmologists gathering to discuss exactly this problem at a conference held in Helsingør, Denmark in April of this year described the scale of the challenge in strikingly candid terms. Researchers presenting updated computer simulations walked through, in real time, just how difficult it has become to build a model of early star and galaxy formation that produces results, matching what Webb keeps finding, adjusting star formation rates and timelines, and still coming up short of the earliest, brightest observed objects. The scientific community's initial, most dramatic reaction in the months immediately following Webb's first deep field results was to ask whether the discovery of unexpectedly bright early galaxies meant something even more radical, that the foundational laws governing how matter and energy behave, the physics underlying the entire cosmological model, might themselves require revision, not just the details of how quickly galaxies assemble within that model. That most extreme interpretation, on further investigation, has not held up as the leading explanation. And it is worth being precise about why, because this is exactly the point where an honest account of the science diverges sharply from the sensational version of the headline. The consensus among cosmologists studying this problem in detail has increasingly settled on a less earth-shattering, though still genuinely significant, explanation. Rather than requiring new laws of physics, these findings most likely indicate that stars form considerably more efficiently and more rapidly in the early universe than existing models of star formation assumed, meaning gas clouds in that era converted into stars at a higher rate, or with fewer of the regulating feedback effects such as radiation pressure and stellar winds slowing down further collapse that normally throttle star formation. In the modern, nearby universe, scientists have had far more time to study directly. Some researchers have gone further, proposing that a population of theoretical objects called dark stars, enormous, extremely luminous objects powered not by ordinary nuclear fusion, but by the annihilation of dark matter particles within their cores, could help account for some of the earliest, brightest, most difficult to explain galaxies, though dark stars themselves remain an unconfirmed, actively debated hypothesis, rather than an established finding. Either way, the emerging picture is one of revision rather than collapse. The broad architecture of Lambda-CDM cosmology, the framework describing an expanding universe shaped predominantly by dark matter and dark energy, remains standing and remains the best available explanation for the large-scale structure of everything astronomers can observe. What is being revised, actively and in real time, is the detailed physics of exactly how efficiently the first generation of stars and galaxies assembled themselves out of the early universe's raw material. A genuinely significant scientific update, but a different kind of claim entirely than the universe's fundamental laws being wrong. That distinction matters, and it is worth sitting with, because physicists revise a model of early star formation efficiency was never going to trend the way James Webb Telescope shatters physics does, even though the underlying science is, if anything, more interesting once you understand what is actually happening. This is what a healthy scientific process looks like when it collides with genuinely surprising data. Not laws. Breaking, but models bending, sometimes considerably, under the weight of observations no one fully anticipated, forcing researchers to build better, more detailed physics to explain what a 6.5-meter mirror pointed at the deep sky keeps finding. Webb's story here is far from finished, and that is perhaps the most important point of all. The telescope launched with enough propellant, thanks to an unusually precise Ariane 5 launch trajectory, to extend its operational lifetime well past its original 10-year design goal, with current estimates suggesting 20 years or more of active service, potentially carrying its observations of the early universe into the 2040s. Every additional year of operation adds more of these early, difficult-to-explain galaxies to the catalog, more spectroscopic confirmations, narrowing down exactly how bright, how massive, and how quickly assembled the earliest structures in the universe actually were. Somewhere in that accumulating data sits the eventual settled explanation for the impossible galaxies problem. Whether it turns out to be more efficient early star formation, exotic dark matter-powered stars, some combination of the two, or a mechanism nobody has proposed yet. What is already certain, regardless of how that explanation eventually resolves, is that the universe's first few hundred million years were far more active, far more complex, and far more surprising than the models built before Webb ever launched allowed for. The laws of physics have not shattered, but the story of how quickly the universe learned to build galaxies out of nothing but hydrogen, helium, and gravity has already had to be substantially rewritten. And the telescope responsible for that rewrite is, by every indication, only getting started. It is worth pausing on how Webb actually pulls off a measurement as demanding as confirming a galaxy's age to within a few hundred million years, at a distance of billions of light years, because the technique itself is almost as remarkable as the discoveries it keeps producing. The first, rougher pass at identifying a distant galaxy candidate relies on something called photometric redshift, essentially estimating an object's distance from how its brightness varies across different infrared filters, since more distant, more redshifted light tends to drop out of bluer filters entirely while remaining visible in redder ones. That method is fast, allowing astronomers to sift through thousands of candidate objects in a single deep field image, but it carries real uncertainty, and photometric estimates have occasionally been revised by hundreds of millions of years, once better data arrived. The gold standard confirmation comes from spectroscopy instead, a slower, more resource-intensive process, where Webb's instruments split a candidate galaxy's light into its full range of individual wavelengths, revealing specific emission lines produced by particular elements, most commonly hydrogen. Because those emission lines sit at very precise, well-known wavelengths when measured in a laboratory on Earth, astronomers can measure exactly how far a distant galaxy's light has been stretched by cosmic expansion by comparing the observed wavelength of a given emission line to its known laboratory value. That stretch factor, the redshift, translates directly into both a distance and, combined with the well-established expansion history of the universe, a cosmic age. It is a method with very little room for ambiguity once the data is in hand, which is exactly why spectroscopically confirmed early galaxies carry so much more weight in this debate than photometric candidates alone, and why so much of the recent controversy has focused specifically on spectroscopically confirmed objects, rather than the larger, less certain population of photometric candidates still awaiting follow-up observation. That rigor also explains why the astronomical community, despite the genuine surprise these findings have generated, has largely avoided the kind of runaway foundations or crumbling panic that a phrase like shattered physics implies. Every claim of an impossibly early, impossibly massive galaxy gets treated as provisional until spectroscopically confirmed, and even after confirmation, researchers spend years cross-checking mass estimates, star formation histories, and structural measurements against independent methods before treating a single object as a settled challenge to existing theory rather than an interesting anomaly awaiting a mundane explanation. Some early, headline-grabbing candidates from Webb's first year of operations have, in fact, been revised. Downward on closer inspection, their apparent mass or age brought back into closer, if still uncomfortable, alignment with standard predictions, once better. Spectroscopic data replaced initial photometric estimates. The current population of confirmed impossible galaxies has survived exactly that kind of scrutiny, which is precisely why it has proven so much harder to explain away. There is also a broader, quieter lesson embedded in this entire episode about how science actually handles the moment a powerful new instrument reveals something nobody predicted. The instinct outside the field is often to treat a surprising result as either confirmation that everything we thought we knew was wrong, or dismiss it entirely as a fluke awaiting correction. What now has actually happened with Webb's early galaxies sits in the far more interesting, far more scientifically honest middle, a genuinely robust, repeatedly confirmed anomaly that has not overturned the broader framework of modern cosmology, but has forced a real, substantive, ongoing revision of one of its component parts, conducted in full public view across dozens of papers and conference presentations by researchers actively disagreeing with each other about the exact mechanism, while agreeing completely on the underlying data. That process, unglamorous as it sounds, compared to a headline promising shattered physics, is the actual mechanism by which astronomy has always advanced, and it is, right now, still very much underway. For anyone watching this story unfold in real time, the most useful habit to adopt is the same one the researchers themselves rely on. Treat each new impossible galaxy not as a verdict, but as a data point still waiting for its full spectroscopic confirmation, its independent cross-check, and its place in a slowly sharpening picture rather than a single, dramatic overturning. That picture, as it stands today, describes an early universe considerably more energetic and precocious than anyone expected going into Webb's launch, one that built massive, structured, occasionally non-rotating galaxies, staged multi-galaxy mergers, and lit up with unexplained ultra-compact objects far sooner than the textbook said it should. Explaining exactly how it managed all of that, without breaking a single established law of physics, may end up being one of the more important scientific stories of this decade. Precisely because the answer has to be found the hard way, model by model, spectrum by spectrum, rather than declared in a single triumphant headline.